next topic, the last short talk in the series is on deep learning, and I'd like to invite our next speaker, Vineet Balasubramaniam, who's a hometown speaker in the sense that he's faculty at IIT Hyderabad. Vineet finished his PhD at the University of Arizona, after which he taught for a couple of years and now is come back to take a faculty position at IIT Hyderabad. So over to you, Vineet. Thank you.
All right, okay. So how many of you in this room work on deep learning, use deep learning, read deep learning? Okay, vote for PJ. Okay. Okay, on behalf of deep learning. All right, okay. Okay, let's get started. We can go to the next slide, please. Thank you. So I think I don't need to talk about this. I mean, I think there's been explosive growth of deep learning in recent years. I think we've all seen applications of deep learning in vision, text, speech. And I think the number of publications in deep learning has been growing over the years. The bottom right graphic that you see there is an interesting graphic there actually. It's Google's graphic on the number of folders on Google servers which hold deep learning models, which I thought was I was just looking for deep learning statistics, and that's one of the ways people have measured how deep learning has grown, but that's an interesting statistic, but that's also going up fairly exponentially. So as I think most of you are working in the space, you don't need this background, but I'll quickly go over this and probably then try to cover what I'm trying to cover on. I think I'll try to focus on today's state of deep learning, which is what I'm intended to be here for. But deep learning has a pretty deep history. So it started with in 1940 with the McCulloch-Pitts model of the neuron. Then came Rosenblatt with the perceptron. Then came the Woodrow-Hoff learning rule in 1960. Unfortunately, Rosenblatt claimed that the perceptron could classify any kind of a function, could approximate any kind of a function. And Minsky and Papert came in 1969 and showed the XOR example and showed that this is not possible. And then came a kind of a dark age for neural networks at that point in time until, say, the mid-80s when backpropagation came into the picture. And again, neural networks took a spike. But probably late 90s and early 2000s, it was dull again until 2006 when Geoffrey Hinton and Ruslan Salakudinov came up with their hierarchical feature learning using restricted Boltzmann machines to train deep belief networks. And since then, I think it's been on an upward trend, and it's now effectively the golden age for deep learning. I'm not going to go more into this. I think there's, of course, a lot of landmark achievements that were in between, like the neocognitron and things like that. But with just this background, what I'll focus on for the rest of my talk today is to actually talk about, I think, okay, one part that I missed, of course, which, oops, I think going back, is that still a problem? Okay. So I think all of us know by now that AlexNet was one of the turning points for deep learning that happened in 2012 when deep learning models won the ImageNet challenge. So what I'll focus on for the rest of the talk today is actually post-2012. Okay, so we won't touch until 2012 what neural networks were. So I've tried to cover the thoughts in my head, and probably I should start with a disclaimer that this talk obviously contains my own bias. So I'm sure each of you here can come and give a talk on deep learning for 20 minutes. So bear with me if it disagrees, and I'll be happy to talk offline if required. So I think I've tried to cover the topics into three parts. One is the consolidation of successes of deep learning over the last few years. So it became successful for computer vision and even before that for speech. So what all have happened in that space and how has that success got consolidated? In some sense, establishing its territory, in that sense. Then I'll talk about exploration of new frontiers, what are the new directions and emerging directions in this space. And of course, I think no talk on deep learning is complete without some deep learning bashing. So we will talk about some limitations, which are challenges and opportunities depending on how you look at it. Okay. So one of the main things that have happened in the last 4 years in deep learning is obviously depth. Okay, that's what the name stands for. So we also saw this in Professor Jawhar's slides yesterday, that I think the ImageNet challenge has been solved by deeper and deeper networks. Every year the depth of the network has been going higher and higher, and it kind of stopped with the residual nets at about 152 layers. And today I think most of the networks, I should say, are in the order of hundreds. And very recently, I think this year there was a last year there was a paper in AAAI which talked about when and why are deep networks better than shallow ones. And they did an empirical study, and I was actually personally surprised to conclude, and in fact I think it's the second paper on this list. The first line of the abstract is yes, they do. Okay, that's That's the first line on the abstract. Okay, so sorry, I think it's the first paper then. Do deep convolutional nets really need to be deep? I think the first line of the abstract is yes, they do. So they actually seem to conclude that you do need depth, okay? Because that's always a debate in the deep learning community, whether you really need all the depth. Can you manage this with some shallower networks, so on and so forth, okay? So that's been one of the, prime components of developments over the last few years. And the depth need not be only along one axis, can also be at the other axis in case of LSTMs. Stack up a lot of LSTMs. I think that's been another trend in deep learning over the last few years is, the understanding, I've probably referenced a paper here that talks about this in more detail. The understanding is that by stacking LSTMs, you're probably learning a more hierarchical feature representation in the data space. And the Google neural machine translation, which goes into Google Translate, actually does use a stacked LSTM in its encoder. Okay. So that's another trend that's been happening in deep learning. The other thing that's happened over the last 4 years is various kinds of hybridizing of architectures, right? So you take CNNs, you take LSTMs, you mix match them, you probably take other components, add them all together and take trained layers from one, untrained layers and mix them up. I think that's been another trend that's actually been happening over the last few years. And that's led to various applications in, say, video captioning, image captioning, video classification, object detection, and many other applications where this has been one of the main themes. So, but I think an interesting thing which probably reflects some of the points covered yesterday too is, I think in all of these efforts, there has been an underlying theme to maintain the end-to-end learning on these architectures. Because as we all understand now, that deep learning is representation learning. So and doing the end-to-end learning kind of helps you with that. Okay? You don't want to, again, go back into handcrafting the features. So doing the end-to-end learning helps you with, learning the features automatically. So that's something that's maintained despite all the modules that you try to bring into whatever architecture that you're trying to put together for deep learning. So to some extent, it's become the mix and match, plug and play kind of an approach at this point in time. Probably very loosely speaking, I can say this is culminated in capsule nets, I think, which is still not, Geoff Hinton's new development in October. I think it's still not caught on much. It has some interesting ideas, but I think it's probably not caught on as much. So the last 4 years have also seen a significant amount of development on the hyperparameter engineering space. A lot of little developments that have taken, an idea like CNN from where it was 4 or 5 years ago to where it is today to solve various kinds of problems. So in terms of regularization, you have dropout, then drop connect, which is a generalization of dropout, batch normalization, or simply just data augmentation or adding noise to the data label or gradient. Okay, so these have all been different ways of doing regularization. In terms of weight initialization, there have again been a bunch of methods today. In fact, I think there was a paper a couple of years back called All You Need is a Good Init. Okay, they show that all you need is a good initialization to get to a good local minima. But I think to this day, a lot of practitioners use what is called the Xavier's or the Glorotz initialization and Kaiming-He's initialization. Then also choosing gradient descent parameters, right? So choosing the learning rate or momentum in your gradient descent process. So that has led to a lot of methods like AdaGrad, RMSProp, ADAM, Nesterov momentum, so on and so forth. Then on the activation functions front, you have rectified linear unit, exponential linear unit, which is more recent, parametric rectified linear unit, so on and so forth. And of course, a variety of loss functions depending on what problem you're trying to solve. And of course, this has a flip side. I mean, a lot of this is hyperparameter engineering to make things work for a particular task. And obviously, that has a flip side. I mean, that is perhaps the elephant in the room for deep learning, is to how do you really choose which parameter to use when. Okay? So we'll revisit that towards the end. And of course, I think the last 4 or 5 years wouldn't be complete without talking about the success of deep reinforcement learning, and the success of it has been reinforced over these years. It started with Atari Breakout in 2013, when not only did the model learn to play the game, but it also learned strategies to build tunnels to go up and hit the roof and bounce off the roof and hit the ceilings and get maximum points. Then of course, in 2016 was AlphaGo, much televised, much followed. I think everybody knew that AlphaGo beat Lee Sedol, the South Korean player, 4-1 on a series of 5 games. But more recently, about a month back, was AlphaZero, which is again DeepMind. All of them were DeepMind's creations. AlphaZero from DeepMind, which played the game of chess. I think to put that in perspective, I think for chess fanatics here, all of you know that Magnus Carlsen is world #1, right? And he has an ELO rating of 2,800, right? So Stockfish is one of the best computer chess playing systems that has an ELO rating of 3,300. So which means if Stockfish played Magnus Carlsen a series of 100 games, Stockfish would beat Magnus Carlsen 95 times. Okay, that's what the difference in 500 ELO points mean. And AlphaZero was trained by playing against itself. Unlike AlphaGo, where there are also heuristics put into the system, AlphaZero was actually trained from scratch by just playing against itself. Nothing else involved in the training. And by training it just for 9 hours, they had AlphaZero play Stockfish a series of 100 games, and AlphaZero beat Stockfish 28-0. Okay, so which has been like a huge revelation for the community because of the fact that it learned to play completely by itself, just by self-play. Okay, nothing else, no strategies, no rules given to it. Okay, of course there's some fine print on the kind of hardware that was used to train these kind of systems, and that's of course a limitation in academic environments. But that's something to be aware of. In addition to these kinds of developments, there's of course been a proliferation of applications of deep learning. I mean, it's everywhere now, especially in the vision, text, and speech space. Very broadly speaking, wherever there is compositionality in your data, deep learning seems to just work very, very well. Like vision, text, speech have some inherent compositionality in them, and it just seems to learn features in these kinds of domains really, really well, as against many other domains. Then we've also seen, obviously with the success of deep learning in many applications, we've also seen proliferation of deep learning frameworks. So now you have a lot of options coming from Google, Facebook, Amazon, and Microsoft. So the graphic on the right, it's a little old. It's about 6 months old. It talks about the most searched framework. I think as of 6 months back, it was TensorFlow. But I think you have to take it with a pinch of salt. These things keep changing with time, and I think there are many other frameworks which are popular, and it depends on the task that you're trying to achieve and what flexibility you want while coding in that framework. And of course, I think this is probably an indication of how strong it is now. I mean, it's in the business space, a lot of startups. We're not going to get into naming any of them, but just plenty of them at this space across the board. I mean, so many application domains at this point. Okay. So let me take a few minutes to also talk about the emerging directions in deep learning, more at an algorithmic level. A lot of these things are still in development and have not gone to a stage of deployment or reaching the consumer, I would say. I mean, again, exceptions always there, but to a large extent. Okay? And I think one of the hottest areas in this space is GANs, like deep generative models. I think generative adversarial networks have been quite hot in the last couple of years. Also, there are other frameworks too, variational autoencoders, pixel CNNs, many other ways of generating images, videos, and of late even text and documents. So in fact, I think there's a pretty popular post on Quora by Jan LeCun that says that adversarial training is the coolest thing since sliced bread. Okay, so I'm quite sure it was an exaggeration, but I think it was meant to say that it's a pretty powerful training method. So many possible applications in this space. Art is an example, and I think there are already some applications out there which use GANs for aesthetics and art. But I think the broader capability of GANs is perhaps the potential to contribute to perhaps unsupervised or semi-supervised learning, where you can probably generate data similar to some data set where you have only limited data and probably train models which can work reliably in a robust manner. Okay? So that, of course, I think that space has been hardly explored at this point in time. The other thing that I mean, people have been trying to do, successful to a limited extent, is transfer learning. How do you take deep learning to newer and newer tasks? Okay, so I think to a large extent, within similar domains, between very similar tasks, it has worked very well. I think everybody takes AlexNet and modifies it to a new vision task and so on and so forth. But I think what we mean by transfer learning here is to take things to new domains where there's very little data, very little annotation, very little expertise even. Okay, so can you actually use deep learning for translating models into these kind of spaces? And of course, some examples here would be zero-shot learning, one-shot learning, few-shot learning, where you have to classify data in one of these classes, but then you don't have any data or have very little data from these classes. Okay, so then how do you transfer models in these kinds of spaces? Another important, I think, algorithmic development that's come about in deep learning in the last few years is the concept of attention and memory. I think it started with natural language processing, I think, in 2015. I think there are better experts here. But since then, it's been used in images and video processing, for captioning, for visual question answering. And also an interesting dimension is to go into memory networks and neural Turing machines, where attention on memory helps you, say, read and write from memory, okay, and kind of simulate a Turing machine using neural networks. So there's been some work there about, I think if you Google neural Turing machines, you can read more about it. So in fact, there's a paper in NIPS 2017 that says that attention is all you need. They say that you don't need RNNs at all. You can kind of achieve networks similar to RNNs with normal networks with just attention. Okay, so that's one of the claims that they have, which broadly makes sense, but hasn't really proven itself. And of course, I think this discussion would be incomplete without the efforts that have propped up in the last couple of years, especially on understanding the theory behind deep learning, and of course, understanding the error surfaces. Finally, deep learning is all about navigating the error surface. That's all deep learning is all about in the training process. So I think the theory of deep learning, last year there was a paper they said they came up with something called the information bottleneck principle. I think I won't go into details today. Okay, you can Google up if you're interested, by someone in Israel, if I'm right, okay, by a group in Israel. And they say that that's the reason why deep learning generalizes well. And more recently, there was also a paper by Kawaguchi, Bengio, and others on trying to study generalization in deep learning. They actually came up with a bound. And they say that the bound actually depends on how many times you validate your deep network on a different validation set, okay, which was interesting, which was an interesting way of studying the generalization. And there's also some work on understanding deep learning using random matrix theory from Google Brain primarily. Okay. In terms of understanding error surfaces, I think there has been a lot of interesting work in this space. So in fact, we do some work in this space too, and I'll be happy to discuss offline about those things. So there was a work by Kawaguchi in MIT on deep learning without poor local minima, where he claimed that under certain conditions, when you have very vast parameter spaces such as in neural networks, all local minima are actually global minima. Okay, they're all global minima. So you either have saddle points or you have global minima. Okay, under certain conditions and constraints, of course. So, but there have been various angles. There is a group, Michael Jordan's group has some papers on how to escape saddle points efficiently using perturbed gradient descent methods, not directly tested on deep learning though, more in the theoretical space at this point. There's also some work on trying to understand what kind of local minima are actually good for deep learning, and there's a paper called Sharp Minima Can Generalize for Deep Nets, where they say that how flat a local minima is helps in telling how generalizable it is. More flat, more generalizable. Okay, so that's what they claim. And they have some interesting work on how do you go from a sharp minima to a flat minima without changing the cost function value, okay, which is an interesting thing again. And of course, another thing here is efficient deep learning. So how do you make deep learning work on edge devices? So we all know AlexNet has about 60 million parameters, which boils down to about 200 MB plus, and VGGNet takes about 500 MB plus. So how do you really make these things efficient on edge devices? Efficiency could mean storage-wise, efficiency could mean compute-wise, could be power-wise, energy-wise, whatever efficient we mean. So there are lots of interest growing in this space, obviously, because I think many companies want to take deep learning to hardware, make it deployable on hardware directly. I think one of the best works in this space has been deep compression from Stanford, which actually won the Best Paper Award in ICLR 2016, where they just had a sequence of a pipeline of simple things which brought down, which got about 50x compression on VGG with zero loss in performance, okay? Absolutely zero loss in performance. Of course, since then there have been many other methods. More recent ones include knowledge distillation, binarized neural nets, and so on and so forth. I think there's a pretty good survey that came out recently on the various kinds of deep model compression and acceleration methods that, if you're interested, you can probably look at. There's also now more recent work on doing deep learning with the input being a graph. So far we have seen text, we have seen speech, we have seen images. What if the input to a neural network is a graph? Okay, so there is, for the last couple of years, again, there's been some interesting traction in this space. There's also a new sub-area emerging called geometric deep learning, which is about how do you do deep learning on non-Euclidean spaces. So again, probably I'll encourage you to go visit that website to know more about it. Or of course, deep learning meets physics. So we'll probably cover this a little bit more in probably the last few slides that I have. So the last few slides that I have is, of course, I think we've all seen it in different forums over the last, since yesterday, as to what are the limitations, why is deep learning not good. So we'll cover a few of these things in the next few slides, and probably I'll stop with that for the next talk. As we've already seen, interpretability and explainability is one of the key limitations. So I think there are two issues here: why deep learning models work and how deep learning models work. I think both are an issue. I think why deep learning models work, I think, is more about the theory and trying to study, its generalization capabilities and things like that. But what we are talking about here is how do deep learning models really work? I mean, how do they work? I think so far most of the effort in this space has been in trying to understand visualizing the weights, probably trying to get a peek a little bit more into, so some of the examples, especially in the image space, has been trying to see if a particular model classified an image as a particular class, okay, what did it really see in that image to give that particular class label? Then you try to identify which portion of the image the model was looking on. So you have some methods such as GradCam. I mean, we have some work called GradCam++ in this space. So I think most of the efforts in this space has been how to, how do you visualize the weights and understand them? There's something called backprop to image, and you play around with the system to do it. But I think what we mean by interpretability is something much, much more. I think there's a long way to go here. I think we talked about it in multiple sessions over the last couple of days. I think what we really want from deep learning networks is to give rationale for decisions, right? It's not, okay, getting a peek into the black box is one step forward, okay, which is great. But I think what we're really looking for is for the deep learning models to rationalize their decisions and tell us why they did something. Okay? And obviously that's when these models would go into healthcare and other risk-sensitive domains where lives could be at stake when a decision is made. Okay? Another important thing is the need for causal inference. So there's a difference between causality and correlation, and it's important to understand that deep learning models capture correlation, not causality. Right? So this is just an example here of a statistic where ice cream sales and shark attacks have very similar statistics between the months of, say, January to November, probably in the Bay Area or someplace like that. And obviously there's no causality here. Okay? Shark attacks is not causing people to go eat ice cream. Okay? So, so obviously there's more to understanding this, understanding causal inference in deep learning. I think there is some recent efforts from Bernard Schalkopp's group in Max Planck. So in fact, they had a paper last CVPR2. But again, a long way to go. Okay, long way to go here in terms of understanding causal relationships in data automatically using deep learning. And I think Professor Raj Reddy spoke yesterday about this, robustness and consistency. Okay, so we already saw this yesterday, where given an image which was classified as the correct label, a little bit of distortion of noise, okay, that's what you see here. It gets classified as an ostrich. Okay, so the third image is an ostrich in all those images. Okay, so in fact, there's another example that they have in the same paper. This was a paper in CVPR of 2015, where all of these images have their corresponding labels, and they were actually classified with 99% confidence. Okay, so you see, as you all can see, you can see a cheetah there and a robin there and a centipede there. Okay, so if you don't, it's your fault, not deep learning's. Okay. But I mean, these set of images were generated by taking just random noise images and adding a small component of what they thought a network learned as a representation of a cat, let's say. Okay, so you can actually do simple things like backprop to image for all cat images and try to understand what is that base image that the network thinks is a cat. Okay, and then you add a small portion of it to a noisy image, and then boom, the network thinks it's a cat now. Okay. So clearly this does not reflect human cognition. So it seems to be learning some discriminative features which it thinks is a cat, and then these are the results that you actually see. Okay? So again, a long way to go in terms of robustness and consistency of results across various kinds of data. Integrating domain knowledge. So this is a recent work last year, 2016, which talked about learning physical intuition of block towers by example, where they tried to build block towers and tried to predict when it would fall. Okay? So an obvious question here is, why don't we integrate physics laws? Why should it be data driven? Okay? So why don't we integrate prior knowledge, why don't we integrate priors? And obviously this also connects to bringing together, say, Bayesian approaches with deep learning. So that's another space that I think that's reasonably open and needs progress. Take one moment. Hyperparameters in engineering. Okay, I think I'll quickly finish. I think all of us know this. This is the elephant in the room. The hardest part of deep learning is to find out what hyperparameters. So this is actually a recent web paper that's to be published, where for a deep reinforcement learning algorithm, they take the same method, 2 implementations, and get results. And they found that the results completely vary with a huge amount of variance. Okay, so which clearly means questions the very reproducibility of these kinds of models across just implementations, okay, not even data sets. Okay, I'll conclude with this last slide. So there's actually a paper called Deep Learning, a Critical Appraisal that came up a couple of weeks back, which seems to be reflecting some thoughts about is deep learning hitting a wall? So there's actually Francois Chollet's comment out there, which says, for most problems where deep learning has enabled transformationally better solutions in vision and speech, we have entered diminishing returns territory in the last year or so. Okay? Of course, from, I think in today's world, about 3 to 6 months, if you don't get good results, that's one generation gone, right? So that's how fast things are going at this point in time. But it seems to, things have slowed down at this point in time in domains where we have known good performance. So that kind of begs the question, while we escape all kind of local minima, saddle points and probably hit better local minima while training, has the field itself hit a local minima? Of course, there, Hinton recently talked about moving beyond backprop, and I think that's potentially another direction to look at. I think I'll stop here. I'm sorry if I exceeded time, and I know we are waiting for the big talk today.
Hello, sir. My question is more of a philosophical. Why we still call deep learning? I mean, we evolved so much and combined unsupervised approaches also, and GAN is handling unsupervised problems and all, and we included meta learning. So
okay, it's just another way of calling neural networks. In fact, Hinton says in one of his interviews that he just wanted to coin a fancy word that makes people take notice. Yeah. So that's how he came up with deep learning. So I think it's finally just a name.
Yeah.
Sir, you discuss about the visual attention. If I will apply deep learning for making the saliency model, saliency map,
sure. So
how we will validate it? Because most of the complex this people 40% most salient, and another 50% is telling region B is the most salient. So how it will be validated, because we don't have the real ground truth?
Sure. I mean, I was talking about visual attention in a different context. I think saliency is a different way of looking at visual attention. In this case, what we are talking about is when let's say you do something like image captioning. Okay? So when you try to caption an image, the typical, I mean, today, one of the most popular approaches is to ask the network to decide on a particular part of the image to look at. Based on that, you come up with a word. Then the network looks at another part of the image, comes up with another word, so on and so forth. And then you string the words together to make a caption. Okay? So the challenge there is to find out which part of the image should my network look at a particular point in time. Okay? So I think there are methods for that. There's something called hard attention, soft attention, and things like that. So that's slightly different from saliency. Okay? Saliency, I think, is a different thing. I think in that case, the labeling is subjective. So that's a separate problem by itself, I think. Maybe we can talk offline about it. I think in those kinds of cases, you'll have to do some kind of crowdsource vote aggregation or something like that to find out, to come up with some kind of a robust ground truth before you evaluate those kinds of models. But today, I think for a large part with all of these methods that model saliency, people just try to subjectively evaluate and see how things work. Okay.
Okay, thank you so much.
Yeah, hi. See, once you have said this thing that deep learning is nothing, but actually the study is related to neural networks only.
Yes, that's correct.
Just wanted to ask the question that if it is related to neural networks, then how much the concepts or the theories established for neural networks are true actually for the real brain as well, where the actual neurons exist? Okay. Is anybody studying, are any kind of studies being made related to that as well?
I think it's broadly understood today that neural networks or deep learning, as we see, are inspired by the human brain, but they don't mimic or emulate or simulate or anything in that context. So I think the model of the neuron and all that is kind of borrowed from the studies on the human brain. But beyond that, I think there is not direct similarity at this point.
Are any scientific groups actually working to make a kind of any kind of similarity or any correlation between the two?
I mean,
Because there has to be a good mix between the medical sciences as well as the computer scientists as well.
I think there is a lot of work, and personally, I think the one group of work that I'm personally aware of is Tommaso Poggio's group in MIT. I think they do some work in this space, but at least I have not seen something convincing in that space, to be honest. I mean, that's my understanding.
If you're available, then I would like to talk to you off the
Sure,
track as
yeah,
well. Thank you so
definitely.
much.
Yeah, thank you.
Okay, are there any more questions for Vineet? Okay, one last. I think people are sometimes shut up, so maybe we should use the time to have a question. Yeah.
Hi, so I want to ask, like, most of the part of your presentation was about like images, and images.
Okay, all right. Okay.
So how about text and other
Sure,
things?
okay. So in fact, there's an interesting thing. I wanted to start with that disclaimer. So of late in machine learning, there's been a lot of discussion about bias in machine learning. So I have to disclaim that I work a little more towards vision. So that's why you had the bias in these slides towards vision. So that was the only reason. Okay? So it's more that I work in vision, so most of the slides were towards vision. But I think maybe if I have a couple of minutes. So if you look a few years back, I think the fields of speech, vision, NLP, all of them were very far away. Each of them had their own conferences. I think the feature extraction used to be so different in these domains that there was not, of course, the machine learning algorithms were similar, but feature extraction used to be so different that there was not much of a crosstalk between these domains. But I think with deep learning and feature extraction being automated, I think the methods that apply to all these domains are kind of coming together. And that's the reason today you have so much of crosstalk between these modalities, because the step that differentiated them, which is feature extraction, is now gone out of the picture, right? So I think a lot of these methods are still relevant to text, but I think there are a lot of experts here on text and speech. I would definitely recommend you to talk to them about. I'm sure they know more than.
Sure, thank you.
Okay, I think we would not hold the next talk any longer. With that, thank you again, Vineet. Give Vineet a big hand. Yeah. And